So we're going to look at the instantaneous center of zero velocity just to give you a little bit more context to what's going on here. Okay, so basically the idea is instantaneous center of zero velocity. First of all, it's really important to note that it is only working for velocity. This does not work for acceleration. Okay, and it's the center of zero velocity. So the idea is if you have this ball and it's rolling like, just rolling. Okay, so this sounds kind of silly. So first of all, this point down here, if we call it just point A, the velocity of A is going to be 0, right? Because the velocity A has to be 0 at this instantaneous moment. So again, this is a snapshot. It's really important because a lot of times people get kind of caught up on that. This is just a snapshot in time. At this snapshot, the velocity of A has to be 0 because if the velocity of A wasn't 0, then it would be spinning around its center and not rolling across. Does that kind of make sense? So if A is moving, then that means it's spinning. If A doesn't move, that's what makes it rolling because there's friction right at that exact moment. Okay, so we have the velocity of A is 0 at this instantaneous moment. Okay, and so then if you think about our equations, we have the velocity of B is the velocity of A plus omega cross R. B with respect to A, so velocity of A is 0, so that just gives us that the velocity of B is just going to be omega cross R, B with respect to A. Okay, because A is our point of instantaneous 0. Instantaneous 0 velocity, that's what I'm trying to say. So what's interesting though is that all these different points, we call them B and B and B and B, they're all moving a different speed, right? So most students can pretty quickly come up with the idea that B, if we call this B, is going this way, that one is just going straight. Like most students are like pretty cool with the idea that, okay, this velocity of this point here is going that direction, okay? And then whenever I ask, okay, well then where is like this point, which direction is that point going? Most people say, oh, it's going straight down at first. But if you think about it, if that one's going straight down, then again, that means that you're spinning and not rolling. Okay, so this is a really big difference. So usually they'll say, well, it's kind of like going this way-ish. And that's right, it is kind of going this way-ish, and not just this way-ish, but this way very, very specifically, it's going this way. Now, whether you realize it or not, when you drew this up at the top, there's a right angle here. And there's still a right angle here. And that actually continues around through everything. Anytime I draw a line from my instantaneous center to a point on that circle, it is going off at a right angle from that position vector. Okay? And so that means you can draw the direction of any vector by just doops and doops. And that last one probably needs to come in a little bit more. But yeah, so see, these all work and go with velocities at right angles. So it's just that omega cross RB with respect to A. So you're getting that answer just by doing the math, but visually, each one of those points is moving forward and A is not moving. So all the points are going with different velocities depending on how far they are around from A. Okay, so that's usually not too bad. And that's not really the point of the problem or this kind of topic. The point of this topic is to locate the instantaneous center if you don't know it. Okay, so basically the idea is if we need to find the instantaneous center, if we just know the velocities of 2 points on the same object, then we can use that information to find the instantaneous center and omega. Now, something that's important to recall is that in general, velocity is equal to omega times r. So if we're not doing things in vectors, if we're just doing things in scalars, velocity is omega r. Okay, so let's say that you had something like this. Like a vector going this direction, and I'm intending to try to make this straight and flat. So let's say we're going here at 8 meters per second, and I'm going over here at 2 meters per second. Now, if I was just going to ask you where the instantaneous center was, like what is this rotating around? What point are these rotating around? And I said it's either going to be A B, or C, like in general, like the general range of A, the general range of B, or the general range of C? Where is it rotating? What is the instantaneous center of rotation? And most people are going to come up eventually with the idea, because at first you might think, oh, it's in the middle. But that doesn't make sense, because if it's in the middle and it's rotating the same amount, then these should be both going the same speed, right? If I'm up here, that makes even less sense, because this one should be going slower. This one should be going a lot faster because it's further away. And so usually, eventually, you kind of get to the idea, well, here this makes the most sense, because if it's rotating a specific amount, then that rotation gets bigger and faster as it expands out from that point. Okay, so in general, we can kind of eyeball it in at point C. Now, we still have to do it mathematically, but at least this gives us an idea of where to do our thinking. So we do have to draw a line. It needs to be perpendicular and perpendicular. It happens to be the same line, so that works. And here's our random point. So we are going to be rotating around omega. Now, I know this is technically a negative rotation. I'm just going to not worry about, I'm going to make sure I've got the signs taken care of. Anyway, so this is an unknown distance here. Oh, I didn't actually tell you how far apart these were, and that's because on my piece of paper I'm looking at, I have a hole punched through it, which is not helpful. Let's say that these are 5 meters apart. Is that good to know? Okay, so these are 5 meters apart. So one distance is d, and that makes the other distance here, say, 5 minus d. Okay, so I know that the velocity of this point up here is going to be given by omega times d, and that has to be 8. And the one down here is the omega times the distance, which is, again, omega times the distance, and that has to be 2. Okay, so I have both of these pieces of information. Now it's really just a college algebra problem of 2 equations and 2 unknowns. So omega is 8 over d, and then I plug that in. So I can say, let's see, hold on, I can do this. This is the part where I always do something dumb. So I have 8 over d times 5 minus d is equal to 2. Let's assume you're not watching this video to watch me do algebra, I hope. And that ends up being something like 40 minus d is equal to 2d, 8d, there we go, see, yay, 10d is equal to 40, and d equals 4, so w equals 2. All right, so what we have is we are now able to actually quickly say that d is equal to 4 meters, and omega is equal to 2 rads per second. And that does make sense, because that means that this distance here is 4. About to write the wrong number. This distance here is 4, this distance here is 1, and that seems like proportionally similar to kind of where we guessed it to be, and it's right. So that's yeah, I mean that's how you do it. Now these problems can get not a whole lot more complicated. It's just a question of kind of playing around with it and getting used to messing around with it. So let's say that I had a velocity here of 8. Try to switch colors. So let's say I had 8 meters per second, and then I had 2 meters per second. And I'll go ahead and do this before I forget. These are 15 meters apart. Okay. So now, if you had to guess, where is the instantaneous center of zero velocity? Where are they rotating around? A, B, or C? A part of you is going to get kind of mad, because you're like, none of that feels right, because if it's rotating around here, or let's just say it's rotating like kind of at C where it was before, then this is going the wrong direction, right? You're like, okay, well, I just need to flip the direction of the rotation, which is fine, except now this one's going the wrong direction. All right, so the answer is actually the center of rotation is not in the middle. The instantaneous center of rotation either needs to be above, somewhere over here, or below, somewhere down here. And again, if you had to guess, you would probably guess that's down here at B. And again, because you're going to have a certain rotation, and as you get further away, you're going to go faster. So we're rotating around some point below because the faster one's on top. Okay, and this is just something that you kind of just have to play with. I think that if you put it on the wrong side, you're going to get negative answers for distance, but I'm not 100% sure because I've never tried doing it wrong on purpose because I was afraid. I'm afraid. So this should be something to get you started. Okay, so at least get it on the right side. And this is where we're going to just say, okay, it's some unknown distance d around, and it's going some omega, or some distance d away and some omega around. All right, so this means that this 2 is going to be given by omega times d, but this 8 is going to be given by omega times the distance 15 plus d, right? Because this d, this 15 is right here. Okay, so again, this is just, we do math, and we end up with d being equal to 5 meters and omega being equal to 0.4 rads per second. Okay, so we're about 5 away. So we're 5 away here, and this is 20 away. Okay, and so that's why you get that kind of like, see how this is 4 times as fast as the other one. The 20 to 5 ratio is also 4. So yeah, so it's consistent. If you kind of look at the numbers, you can kind of see where it's coming from. Now, if the velocities are not parallel to each other, the geometry gets more complicated, but it's basically the same thing. So like if I had a 16 meters per second here and a 6 meters per second over here, and I'm going to specifically tell you that this distance is 7 meters at a 30-degree angle. Okay, so there's, I mean, it's just geometry problem now, and I don't mean to minimize it as saying it's just a geometry problem, but it's just a geometry problem. So if you're trying to find where the instantaneous center of zero velocity is, you're just going to draw a line perpendicular. So here, let's see if I can do a nice perpendicular line. A nice perpendicular line here. Now I could draw my perpendicular line here if I wanted, but then that looks weird because it's really close. I wouldn't recommend drawing your lines so that they intersect on one of the vectors, because that just, visually it's more complicated. It's not technically incorrect, but you're going to argue with yourself a lot over it. So then I'm going to pick another one. So this is going to be a right angle here and a right angle here. And you're probably feeling like, well, if you draw it down here, it's going to be further away, but it's all going to proportion out. And that's really what we're doing here, is we're doing the law of proportions. So you can totally draw yours all the way down here. You're going to get the exact same answer I'm getting. And you get the same answer, honestly, if you drew it right on, for example, on the 16, it would just, I mean, you just need some kind of a distance to, I mean, not directly on the 16, but as close as you get. You just need some kind of a distance to make it work. So basically, I'm going to draw in this little triangle here, because this is just an example of the geometry. All the geometry is going to be different potentially, but this is just to let you know kind of how this works. So there's a lot of ways to do this. I'm going to do this by labeling this little distance right here d, and that makes this distance here 7 minus d. Since that's a 30-degree angle, then that makes this a 60. And so now it looks like a 60d. All right, so this is a 60. Let me zoom in. I have this capability. All right, yay, look at me solving basic problems. So if this is a 60 and this distance here is d, then this is my 30. And so this is 2d and, you know, d root 3. I don't think I care about that, but those are my distances now. Okay. And we're still going around. Now, I'm specifically drawing my omega this direction because that just keeps all my numbers positive. So I'm going omega because that matches the direction of this arrow and it matches the direction of that arrow. Okay, so if your arrows are going the other direction, you can draw your omega going the other direction as well. Okay, I'm just drawing them that way. Okay, so the 16 is 2d away, and the, what do you call it? The rotation is omega. The 6 meters per second is 7 minus d away, and it's also going omega radians per second. So I've got that 16 is equal to 2 dw, or 8 is equal to w omega d. I keep calling it w. I've got 6 is equal to 7 omega minus omega d, and then I can math, and I get that d is equal to 4 and omega, so 4 meters, and omega is equal to 2 rads per second. Now I'm getting pretty answers because I designed these problems to get pretty answers. You're not always going to get pretty answers, but kind of look at this and see if it feels right. So I drew it really, really, really close, but in fact, in reality, it was a lot further away. Let me kind of, so this was the 16 and this was the 6. It actually is even further down. If I was going to try to be real to scale about it, out of the fact that this is d and 4, I would probably need to be kind of closer to here. So this was the distance 7 that was given. So this was the distance 7 that was given. This distance here is 4, so 4 and 3. Okay, so this distance is 8. Okay, so like that. Okay, and it's going around at a rate of 2. Okay, so 2 times 8 gives me 16, and 2 times 3 gives me 6. Okay, so that's how these numbers are related. It's a little weird looking. Notice it's not 2 times 4, okay, because that's just a it's just a distance that doesn't really have any meaning. We're looking for the perpendicular distance to the velocity vector, and that 4 is not perpendicular to the velocity vector. It's off at 30 degrees. So so yeah, this is all kinds of crazy and fun, but this should kind of give you a good framework to start looking at these. And again, the most important thing is you can't use any of this theory for acceleration.